Welcome to the next lecture of this module. And in this particular lecture, we'll be talking about the next model, that is polynomial linear regression, which is an advanced version of linear regression. Till now, we have studied all the maths, implementation, and we have coded linear regression from scratch. And in this particular lecture, we'll be talking about why we need to use polynomial regression and what are the advantages to use it and all the maths involved behind. So with all this, let's start with our lecture. So first of all, hypothesis. Whenever we are talking about any model, we are concerned about its hypothesis. As in case of linear regression, the hypothesis was very simple. Y is equals to mx plus c, right? Where y is the output, x was the input, and m and c were the weights. Initially, we randomly initialize our weights and then we optimize those weights using gradient descent algorithm, right? And then we reach on to a final hypothesis where we have the most optimal values of m and c to predict our input values. Now in case of polynomial linear regression, the hypothesis is somewhat different. Okay, so here it is, y is equals to, where theta is a weight. Okay, so theta naught plus theta 1 x1 plus theta 2 x1 up to, where it's raised to the power of 2, up to theta n x1 raised to the power of n, right? So this is the hypothesis which we are talking about in polynomial linear regression, right? Depending on the dimension we need, these can carry on. So if we need n dimensions, then we'll be having n plus 1 weights, right? So these are all weights and we have only one input over here, so the input is x1. Okay, and these powers 2, and this describe the dimensions in which we are going on, or the linearity, because we are trying to involve the non-linearity in case of polynomial regression. So we need to have these powers. When we were talking about y equals to mx plus c, this was a linear equation. There was no non-linearity. Okay, so wait a second, I'll explain what I'm talking about linearity and non-linearity. So coming to the use of polynomial regression, I have already told you that we are targeting to have non-linearity in our models. In case of linear regression model, the hypothesis was only a straight line. But what if we have our data points marked like this way? So if we get the most optimal linear regression, we will miss all these points, right? Or suppose if it is like this, so we can't have a linear structure over here. We need to introduce some non-linearity. So in that case, we want our hypothesis to be exact like this, right? If we have such kind of hypothesis at the time of training, you can see that we have introduced non-linearity over here, and this particular hypothesis is fitting the best. How much we train our model, linear regression can't be fit on such a data set because we have a linear structure over here. There is no non-linearity in it. And based on this hypothesis, our equation will be of the form y equals to theta naught plus theta 1 x1 plus theta 2 x1 raised to the power of 2, right? So this will be the equation of this particular hypothesis, and this theta 2 x1 square part is involved for the parabolic function of our hypothesis, right? So this is why we need to introduce non-linearity to our hypothesis, because in real life data set we won't be having so much easy data to fit a non-linear hypothesis in it. How much we train our linear regression model, it can just shift its position. It can't adjust this hypothesis over these data points, right? So in that case, this particular polynomial linear regression hypothesis will work much better than the linear regression model, right? But the question arises, if we have a non-linearity in it, why are we saying that it is a polynomial linear regression? Why we are focusing on linear, and why we are saying that it is the advantage over linear regression model? Well, the basic reason is, look at this equation again, y equals to theta naught plus theta 1 x1 plus theta 2 x1 square plus up to theta n x1 raised to the power of n. Sorry, it's n. Okay. So now just focus on the weights. The weights we are finding in polynomial linear regression, we are supposing it to be a linear model because of these weights only. They are having a power of 1 only. But if you are saying that this was a quadratic equation or an n-dimensional equation, it was because of the inputs, not because of the weights. And when we are talking about the hypothesis, we are concerned for the parameters, right? That is the weights. So here the theta is always a linear parameter which we are trying to find, which we are trying to predict, right? So this is the very basic reason that polynomial linear regression is named as an advanced version of linear regression, because it can introduce non-linearity to the model, also retaining the linear function of the hypothesis because of the weights. The weights involved are still linear, and the non-linearity or the parabolic function is being introduced because of this particular parameters, where inputs are raised to the power of something because of the dimension or the degree of non-linearity we require. So in case of a parabolic function, we were having equation till this point only because this was sufficient to fit our data well, right? So this was the hypothesis behind the polynomial linear regression model, and rest the updation of the parameters, back propagation, cost function minimization, all work similar as linear regression. It's just that when we are updating our parameters, then in case of linear regression, we have two parameters m and c, but here we can have number of different parameters, which is theta naught, theta 1 up to theta n. So we have to find the updated parameter value for all these functions, and and the cost function will remain same. We will compare the y predicted value with our actual output value, right? So this was all about polynomial linear regression. This is why we call it a linear regression model advantage, and this was the hypothesis involved. As I told you in the previous lecture, that polynomial regression is an advanced version of linear regression, right? So in this particular lecture, we'll be coding that polynomial regression, and we'll be understanding all the concepts that we have learned in the previous lecture. So I have already written this code because it's almost same like the linear regression one. I'll show you the changes that we have to make. So here we are loading our library, Panda, NumPy and Matplotlib, and now we are loading our data. This data is similar to the one that we have used in linear regression, right? And now what we'll do is we'll explore our data as we have done in the linear regression part. So data.head. So you can see that we have two input. We have an input and an output, x and y, right? And the data info, which will show you the number of data entries we have. So we have total 700 entries, and we have 700 input and 699 output. That means there is a null value in our output column. So we'll drop that null value, because removing one entry from such a data won't hamper our data distribution, so we can do that. So for that, I'll be using drop NA function as we have done in linear regression, and we are getting the shape. So now we have 699 entries and 2 columns. So again, let's check the info. So now you can see that we have 699 entries, each in both the columns. So now we have no null values. So what we have done over here is we have distributed our input and output to training input, training output, and testing input, testing output. So for training part, I have used first 500 entries. So first 500 entries of X in train input and first 500 entries of output in train output. and the remaining entries I am using in test input and test output. So let's check the shape. So now you can see that we have 500 entries for train, 500 entries for train output, 199 entries for test input and test output, right? So now it's time to modify a linear regression model using the polynomial regression technique. Okay, so what we have understand in the intuition lecture is that this particular polynomial regression model is an advanced version of linear regression where we introduce dimensions to our input, right? So in case of linear regression, our hypothesis was y equals to mx plus c, or you can say theta naught plus theta 1 x1. But in case of polynomial regression, our hypothesis is like theta naught plus theta 1 x1 up to theta n x1 raised to the power n, right? So we have in single input but with different powers. That power describes the dimension and the non-linearity concept that we want to introduce. And the theta are the weights which are still in linear position. That's why it's named polynomial linear regression. Polynomial because we are introducing non-linearity to our input so as to change our hypothesis as to make it non-linear, but linear, but we are saying it linear because the weights are still having the single degree, right? So let's code our model. For that, what we'll do is we'll import our linear regression. Okay, so from sklearn dot linear model import linear regression, right? And now we'll import our polynomial function also. So for that, again using scikit-learn, but now we'll use the pre-processing module. So from sklearn dot pre-processing import polynomial features, right? We have imported both these libraries, and now what we'll do is poly regressor. Now we'll initialize this polynomial feature function and let's name it as polynomial regressor. Okay, so polynomial regressor and polynomial features. Now we have to select the degree. So if I select degree equals to 2, that means we are implementing the same function that we did in the intuition part, that is theta naught plus theta 1 x1 plus theta 2 x1 raised to the power of 2, and then the equation will stop because we have introducing only 2 degrees. So that's how the degree function works. It means the kind of non-linearity we want to introduce. So let's set our degree to be 2. Okay, you can get an intuition of this degree function by plotting your data into an Excel sheet and then finding the kind of graph you want to make. So let's first of all do it in a hit and trial method. Let's set our degree to be 2. Okay, and now let's name our data that will be prepared. Our target is to basically prepare the weight matrix, right? We have hypothesis theta naught plus theta 1 x1 plus theta 2 x1 raised to the power of 2. You can also set it like theta naught x naught, since it is x naught raised to the power of 0, x1 raised to the power of 0, so it will be 1. So that's why it's theta naught only, plus theta 1 x1 plus theta 2 x1 square. So we have to implement a matrix where we have n cross m shape. N means total number of entries and m describes the degree we want. So it will be x naught, x1 raised to the power of 0, x1 raised to the power of 1 and x1 raised to the power of 2. Let's implement it with the help of code. So let's name that input as, the matrix we want is train input poly. Okay, and now what we'll do is we'll use this regressor that we have initialized over here, and now we want to fit transform our data. Fit transform, because first I want to fit my poly regressor over that input data I have, and then I want to transform it to the matrix that I want, x1 raised to the power of 2, x1 raised to the power of 1 and then x1 raised to the power of 2. Okay, so we'll be fitting our X, that is train input, right? So now we'll initialize our poly regressor. We'll fit this data to our poly regressor. Okay, so poly regressor dot fit, and then we'll fit our train input data and train output data. Okay, sorry. So here we go. We have initialized our polynomial regressor. It has degree equals to 2. You can check this particular, wait a second, you can check this particular train input poly. You will be seeing that, let me tell you the shape of it also. So basically we have 500 entries in input, and this train input poly has 3 columns. Why 3 columns? Let me show you. Because now our data is x1 raised to the power of 0, which is all 1, then x1, then x1 raised to the power of 2. Okay, so this is how we build up the metrics that we want. These are the polynomial features that we have now, and now we will be fitting these polynomial features to the linear regression, because it is a modification over linear regression. So we are modifying our features using the polynomial features, and rest, the upgradation of parameters, gradient descent, all will go as in case of linear regression. The modification over linear regression, we have performed it over here, right, in this particular column, and now we will be implementing the linear regression. But the difference is, wait, linear regression equals to linear copy equals to linear regression. We have initialized the linear regression, and now we'll say that linear regressor, let's name it as linear regressor, okay, because otherwise it will create a confusion. So linear regressor, and now we'll fit our data, but the trick is, now we won't be fitting our actual input and output data. Here we'll be fitting the transformed features we have. So the transformed feature is train input poly, right? So we'll copy this train input poly, and what we'll do is we'll say train output, right? So now we are fitting the input and output data, but the input data now we have is this particular data. Why? Because we need to implement a different hypothesis. So this will be our hypothesis, and now we'll be having 3 weights, theta naught, theta 1, theta 2, and our gradient descent will work 3 times to update these 3 parameters. Rest, the cost function calculation and the updation of parameters will go the similar manner like linear regression does in case of 2 parameters, right? So this is how we fit our linear regression model by using the polynomial features. Okay, so it's running. So we are done with it. Our linear regression model is all ready. Now we are ready to perform the prediction. So for that, let's name the predicted values as predicted value only. And now we'll use this regressor, which is we have fit over our data. And now I'll say predict. What we want to predict? We want to predict the test input value. But the test input value also, we have to build up a similar matrix that we have built it over here, because otherwise the hypothesis can't work over that model, right? Because when you were predicting the value y predicted equals to mx plus c, there you have 2 parameters m and c. Similarly, in this case also, I have to maintain a similar hypothesis, and then the predicted value will be compared with the actual output value. So for that, what I'll do is I'll say poly regressor dot fit transform my test input, right? So in the similar manner that we have transformed our train input, we will transform our test input. It's just that we are building up this particular matrix, right? So that we can use our weights accordingly, because at the end what will happen is matrix multiplication. Theta naught will multiply with the x1 raised to the power of 2, theta 1 will multiply with the x1 raised to the power of 1, and theta 2 will multiply with the x2 raised to the power of 2, and all will add up. So here we go. We'll predict a value. Okay, I have done a spelling mistake over here. So it's poly. So we are done with our prediction, and now we'll calculate the error that we have in our predicted values. So for that we'll use from sklearn dot matrices import mean squared error, right? And let's check the error equals to, copy this mean squared error. Now to calculate the mean squared error, what we want is predicted value and the actual test output value. So predicted value and the actual test output value, right? So let's check it. Done. Let's find out the error we have. So we have an error of around 8%. That means we are predicting our values with an accuracy of 92%, which is a good thing. So you need not to worry about that we are getting a less accuracy or not. We can change this degree over here. These are basically the hyperparameters. So before finalizing our model, we check over all these hyperparameters or different combinations we can have to get the best accurate model, right? So this is how we build up a polynomial regression model, and you can also visualize it using matplotlib. So let's do it. So let's name it as, first of all, what I want to plot, I'll plot the actual hypothesis and the hypothesis that we have with the polynomial regression. So the actual hypothesis will be test input and test output, right? And then symbol plus and color equals to green. Okay, and now we'll plot plt dot plot the hypothesis that our polynomial regression is working over. So for that we'll say test input versus the predicted output. So it was predicted value, sorry, and let's the symbol be a star. Okay, and let's color it red. So the green one will be our actual hypothesis and the red one will be our predicted hypothesis, and we are comparing both. Let's name the function graph as polygraph. Okay, you can also label the x label and y label. So plt dot x label as input and plt dot y label as output. As simple as that. Sorry, label. So output, right? And then plt dot show. So here we go. This red line is the actual hypothesis and this green one was the predicted hypothesis. Here in this case you need not to basically have a polyregressor because we don't want too much of non-linearity over here, but this lecture was just for the intuition of yours that how we can build up a polynomial regression. If you have a data which will be having a non-linearity, this model you can see that hypothesis in a much more well-defined manner that it will be having a non-linearity. And here it's working very good. It has predicted the value with an accuracy of 92%, and the green one is the actual hypothesis and the red one is the predicted hypothesis, which is almost lying over it, right? So this was all for this lecture. We are done with the polynomial regression model. We have learned the hypothesis, the advancement over linear regression model, and the implementation of this polynomial regression model so as to make it advance over linear regression. So this was all in this lecture. Thanks for watching this lecture and keep following.